Okay, folks, we're going to pick it up here, right where I left it off. So, let's see here. Okay, so in that first video, we went over the definitions of energy, heat, work, potential energy, isolated system, closed system. So know all of those definitions. Be familiar with them, okay? Understand the difference between exothermic and endothermic, as well as the sign. So positive or negative. Negative is always exo, positive is always endo. And be able to apply that for delta E, Q, or W. So this is really a big one. This learning goal number 2 is a big one for this chapter, all right? Number 3, know the equation for the first law of thermodynamics and how to perform simple calculations with heat and work. So I gave you, actually we didn't do any of these. So we're gonna focus on some of these calculations in our discussion section. And by simple, I just mean, you know, this plus this, or this minus this, okay? So we'll have some examples of this in discussion. And I pushed forward and made it through learning goal 4, know how to perform PV work calculations using the appropriate units and conversion. So it's a simple formula. It's just knowing how to do the right conversions, knowing how to identify the right final or initial conversion. Okay, so moving forward, so this video, I think I'm only going to cover this learning goal 5 because this is a big one. So know what enthalpy is in all of its various forms, as well as be able to perform simple calculations. Okay, so we'll do this one today. This is a big one just for this learning goal number 5. Okay, so let's see. So what is enthalpy? Okay, so I'll remind you that in the first law of thermodynamics, okay, delta E is Q plus W. Okay? Well, what happens when there's no change in pressure? Or no change in volume. So we'll say no change in PV. Okay? Then is there any work done? Nope. So work goes to 0. Okay? So if there's no change in pressure or volume, then we call that little subscript P right there, that denotes constant pressure. Okay? And now specifically this heat that we're delivering at constant pressure, we define as enthalpy. Okay? So as you can tell, it's going to have the same units as all of the other stuff, joules and or kilojoules. Okay? But specifically, enthalpy is the heat absorbed by an endothermic process or given off by an exothermic process occurring at constant pressure. So these can be chemical or physical changes, all right? And so when we talk about enthalpy in chemistry, it's kind of a blanket or like an umbrella term for a lot of different things, okay? So it's the heat accompanied with physical or chemical changes occurring at constant pressure. And so why constant pressure? What's the big deal about that? Well, if you think about how we do things in a laboratory, right, where we're mixing beakers and stuff, the pressure is constant, right? We're not doing things in a balloon. We're not doing things up at the International Space Station. We're not doing things at the bottom of the ocean where we're like moving up and down and changing pressure rapidly. We do 99% of our chemistry at a lab bench where pressure is constant. Okay? So we have this term called enthalpy, which is just a blanket term for heat. It's just a type of heat. But specifically, okay, capital letter, it's a state function. So with respect to enthalpy, we only care about the final state and the initial state. You guessed it, okay? So here's some examples, okay? So we talked about phase changes earlier and how there's going to be heat either leaving a phase or having to go into a phase. So for example, to melt ice, as it turns out, it takes positive 6.01 kilojoules for every mole of ice to melt. Okay, so this delta H fuse, we put that little subscript fuse for fusion, or I could write this as the delta H of melting, for example. We also have delta H of vaporization, delta H vape. I could also call that delta H of boiling if I wanted. So that gives me the actual quantity of energy I need to boil an amount of water. So I need positive, right, because the heat has to go into the water to melt it, or to boil it, for this example. 40.67 kilojoules for every mole, right? So if, let's say, I want to melt, or excuse me, let's say I want to boil 2 moles of water. Suppose I want to boil 2 moles of water. Then I'm going to multiply this by 2 moles, and let's say 40.67 times 2, meaning I would have to supply my 2 moles of water with 81.34 kilojoules of heat. Okay? So that's what's useful about these delta H's. They allow us to calculate or predict how much energy we need to do something. So what's also pretty cool about this, and again, this is less intuitive, I think, but so if it takes 40.67 kilojoules to boil water, if I were to now condense water, I get the same quantity of heat back out into the surroundings, which you don't really think about, but it's true. When you condense some water, there's a huge amount of heat that gets released. We often call this the latent heat. Latent, am I spelling this correctly? I'm a terrible speller. Latent, oh my God, now I'm having a brain fade moment. Latent heat of evaporation or condensation, okay? So this is happening in the atmosphere all the time when you think about weather systems occurring on big, massive scales, all of this water condensing in the form of rain, and it releases a ton of heat back out into the atmosphere, okay? Or similarly, when all of that liquid water fuses into a solid or freezes, okay? There's a lot of release of heat, that negative sign, okay? So we want to use these quantities, these energy quantities per mole, in the same way we've used every other quantity in this class via the process of dimensional analysis, okay? So here's some other examples of chemical changes in enthalpy. So this is the same slide I showed you before, but now, based on this, there is a release of heat, and specifically for this reaction, the delta H, and I'll write delta H, and I like to write RXN for reaction. Okay, for this reaction, it's negative 242 kilojoules for every mole combusted. All right, so this is global for the reaction, but let's suppose we look at this for the 2 moles of water created, right? How much energy will be released? Well, in the same way I did that other calculation, right? If I make 2 moles of water from this reaction, the energy released will actually be 2 times this number, okay? Because this number is the amount of energy released per mole of reactant or product, right? But now for the way that the reaction is written, if 2 moles of H2O are created, then I'm going to have, what is that, negative 4 kilojoules of total energy released. So again, pay attention to that per mole quantity. So what if I had 18.562 grams of water created in this reaction? Well, then we would go through and do our stoichiometry, and I'm going to give you an example of that soon. Okay? So here are all of our various flavors of enthalpy. So I'll remind you, that's what we talked about in the learning goals. Know what enthalpy is in all of its various forms. Okay? So here's 4 examples that I'm going to give you. There's the standard enthalpy of formation, the heat of formation, delta HF. This little 0 right here, that means standard. And that standard means it's occurring at room temperature. Okay? So that is the heat that would be released for this reaction at 298 K. So when we see that little superscript 0, that means standard. That little F in this case for this flavor means formation. And what is the enthalpy of formation? Well, it's the change in enthalpy that accompanies the formation of 1 mole of a compound from all of its elements with all their substances in their standard state. What does standard state mean? I'm going to review this again, but standard state means what phase is that substance at 298 Kelvin. Okay? So for example, this, as it turns out, this reaction is the standard enthalpy of formation of H2O. And really we'd have to write it as H2 gas, that's the standard state, plus 1/2 O2 gas. Oxygen is a gas at room temperature, and this would make 1 single mole of H2O. Okay? So this would give me the delta H of formation of water, and that's 242 kilojoules per mole. With 1 mole, it'd take 242 kilojoules to form water from its elements at standard state. Okay, so that's what delta HF means. Well, delta H reaction, this next one, and again, I often like to write that as RXN as an abbreviation, with the little standard, of course, if that's occurring at 298. So that's very similar to this heat of formation, but now that's the change in enthalpy that accompanies any chemical reaction. So it doesn't have to be the chemical reaction written in a standard state from its standard elements. So for example, this just so happens to be a chemical reaction, right? So I could say delta HF or delta HRXN for this particular reaction, because again, this is a reaction that's forming water from its elements at standard state. However, I can also use this delta H reaction for any old generic reaction that we might encounter in this class. Doesn't have to be a reaction forming the compound from its elements in their standard states. All right. So, and then we talked about these two, delta H of vape and delta H of fusion. So this delta H of vape is the standard enthalpy of vaporization, or the heat of vaporization. So the change in enthalpy that accompanies evaporating 1 mole of liquid. Or delta H of fusion, the change in enthalpy that accompanies melting 1 mole of a solid. And again, because these quantities are per mole, right, they're all some kilojoule per mole, okay, I recognize that I can do this process of stoichiometry with this quantity, right, depending on what I'm given in a problem, okay? So suppose I'm given grams or milliliters or whatever, right? So I can use that in my dimensional analysis to do these types of calculations, okay? So let's do a sample problem, all right? So the flame in a torch used to cut metal is produced by burning acetylene in pure oxygen. Cool, so acetylene, C2H2, right? This is combustion. You guys know how to do combustion reactions. So it's gonna make carbon dioxide and water. We don't need the reaction for this problem, but I'm going to write it anyways just to demonstrate that it's something we've already seen. So I need a 2 right there to balance it. And now that gives me, let's see, 2 times 2 is 4, plus 1 is 5. So with the 2 right there, very quick math, I need 5 halves. And now that is all balanced. And I wanted to balance this specifically for 1 mole of acetylene. Okay? And I didn't have to do that for the reaction, but I'm balancing it in this way just to demonstrate to you what's going on. Okay? And so this reaction, so I'm going to write the delta H of the reaction next to it. So it says releases. So this is key. It releases. So that tells me delta H has to be negative 1251 kilojoules for every 1 mole. So I'm going to say per mole. And I've balanced the reaction for 1 mole. So I'm good to go there. Okay? So now it says what mass of acetylene is needed to cut through a piece of steel if the process requires 5.42 times 10 to the 4th kilojoules of energy. Okay, so how are we going to do it? So I am trying to get to this quantity of energy, 5.42 kilojoules. So I'm going to start with that number. Okay, just like in our process of dimensional analysis, start with what you have or what you need in this case. So what I need in this case is 5.42 times 10 to the 4th kilojoules. And notice that's not kilojoules per anything. That's just kilojoules. Okay? So how am I going to get to that? Well, look. Here is where I can use my number here, just like I do in any old dimensional analysis problem. Okay? So I'm trying to get to what mass. So what mass means how many grams, for example. And so I want to convert this energy into moles. And I can do that by using this number. And I'm going to try to cancel the kilojoules, right, because I'm using it in my dimensional analysis, 1251 kilojoules. And here's the tricky part of thermo, because we notice that it's a negative sign for the delta H. But in this problem here, I'm just going to use the absolute value of that number because I'm trying to convert this energy into a mass. So I need to convert it into mass. So that means I don't need the negative sign because you can't have negative mass, right? And so the way this works, because it was 1251 kilojoules over 1 mole, I can also say that that's 1 mole over 1251 kilojoules. And now specifically, that's 1 mole of C2H2, of acetylene, right? And if I look this up on my periodic table really quick, 12.01 for carbon, 1.008 for oxygen, I get that that's 26.04 grams of acetylene for every mole. So the mole and the mole cancels, the kilojoule and the kilojoule cancels. And now I can go and do this problem here. Let's see, 5.42 e to the 4th times 26.04 equals, divided by 1251 equals, and with, let's see, 3 significant digits, 1, 2, 3. This one had 1, 2, 3, 4, but I used 3 because that's the least. That's going to be 1.13 times 10 to the 3 grams, 1, 2, 3, or 1.13 kilograms, okay? Okay, so again, to summarize, we can use these delta H values just like any other quantity we've used in our dimensional analysis, okay? When we have the delta H of a reaction, we recognize that's kilojoules per mole of any one reactant, okay? So in this reaction, if 1 mole of acetylene is consumed, I get 1251 kilojoules, all right? So that's how that works, okay, from the perspective of the acetylene, all right? And so that means since that's my fuel source, then really that's what I need to use. It's not about how much CO2 I make or how much H2O I make, because I'm using this reaction to generate energy. And so the acetylene is my fuel. So that's really like how much I need to consider using for this reactant. Okay? So that's why we're asking what mass of acetylene is needed to use. All right? So let's see here. So I think that's actually a pretty good place to cut it off, and we'll get a lot more practice with these types of things in the discussion worksheet. All right? Okay, folks. Hasta luego.